Hello and welcome, everybody. I already see that we have a huge crowd, or a big part of the people registered are already in the webinar. So I would like to start on time and share some of my knowledge about circular economy of plastics with you. And the topic of the webinar today is how to make the most of mixed recycling streams. I hope you all enjoy the next 30 to 40 minutes, and I hope we have a lively discussion afterwards. First, a couple of words about myself and giving you some background on why I'm presenting what I'm presenting today. I'm the business field manager polymer here at Netsch Analyzing and Testing, and I started in that role beginning of last year. And before that, I had various positions in academia and industry, and in some of these positions, I had also. I just received the message that not everybody can hear me. If you can hear me, could you just put that in the. Oh, perfect. Sorry that I think everything's okay, and I'll just continue. So I just wanted to explain that in various of these roles, I was working on plastics recycling, composite recycling, and as part of the research I was doing as a professor at the University of Wisconsin-Madison, we did intensive studies on the technical aspects of a circular economy of plastics, and also economical and ecological benefits. And out of that that work, two of my graduate students and I co-authored a book, Understanding Plastics Recycling, and you will see some of the graphs are out of that book. Just to give you the context. And with that, I would like to dive in, talking a little bit more about circular economy of plastics. Then we talk about recycling streams, different methods. And as I'm talking about all of these, I want to give you an overview how thermal analysis and rheology in particular can be used to analyze, characterize, identify your material, and understand the processing behavior. I'm not going to talk in very much detail how the individual measurements are performed, but I invite you and encourage you to ask me questions afterwards, and also put that in your questions if you're interested in learning more about that, and we'll put out additional webinars and content for you in the future. So I highly encourage you to use the question box to let us know what other topics you're interested in. When we talk about circular economy, we really want to get away from that model of you take material, you make a product out of it, and at the end of the life you discard it, and you start with new feedstock. Circular economy is really trying to get into a cycle where the material is used and reused and recycled as many times as possible, ideally a never-ending cycle. So I want to start with the typical plastics production. So we have our material produced, then we manufacture a product. It goes through the use phase, and then after its service life, the approach of circular economy thinks of ways to reuse that product for a different purpose, or repair it and continue its use. Or we think of recycling, and we have different routes of recycling if we can reuse and repair the material. The one that is used significantly in the European Union is energy recovery, so burning it for energy, because plastic in itself has still a very high heat content. But there are also issues associated with volatiles and ecological issues. Then the typical recycling route that we mostly talk about is mechanical recycling, where we collect that material and grind it and reuse it in new products. So we omit the plastics production, and we don't need to use new material. We often call that virgin material, but we use this regrind is in 100% or mixed with virgin material to produce new products. And then last but not least, we can have chemical recycling. A lot of the material suppliers are active in that field, where we break down the plastic, which are polymer chains, into smaller oligomers or monomers, and create new raw material to produce plastics out of it. And then part of the circular economy is also to use renewable feedstock, bioplastics. And what we really want to avoid is that anything goes into landfill, and definitely not illegal dumping and littering. The only cycle that isn't really shown here, what I just explained, is the post-consumer waste, but we can also have a separate cycle here in product manufacturing, where we use our production scrap, or what we call the pre-consumer waste. And often that is done with mechanical recycling, and we regrind it. It's really, that's what the industry is doing today. There's hardly any plastics manufacturers that don't do anything with the material. When we look at the distribution of global plastics production, a lot of you are familiar with these numbers, because yearly they are published by Plastics Europe, and that's why I'm showing them mostly for Europe. We have a distribution of the global plastics production, which is highly centered in Asia, and we also have a proportion in the Americas and some in Europe, but Asia and China are really the biggest producers. And what are we producing in 2019? The same as many years before. 50% of all the plastics produced are polyolefins. The highest number is polypropylene, and LDPE and HDPE, and then all the other plastic materials make up the other 50%. And the reason why we use so many polyolefins are really when we look at the plastic demand by industry. You can see that packaging makes up 40% of all the plastic products produced. That's a high amount. It equals roughly 20 million tons of plastic. And by the bubble size that you can see here, it's quite obvious that in packaging, the majority of material used are polyolefins. And that's why they make up that big chunk in the plastics production. Then packaging is followed by building and construction. That's 20%. So already half of the volume that is produced by packaging. And then another half of the building and construction is automotive. And then we really get down to smaller portions. Even so, these industries are really big. The plastics consumption is really mostly contributed or used in packaging, building and construction, and automotive. And that explains also why some materials are produced more than others. And since I wanted to talk about mixed streams and mixed products, I took some common polymers in the category of packaging, electrical, electronics, and automotive to give you an idea what the typical materials are. So in packaging, for example, I picked the example of bottles and films, and you can see we have a variety of materials that can be used. So even if you wanted to sort out all the bottles, you could still have at least 5 different materials in varying portions. The same with films. You have a lot of different materials that are used for films. And one problem in all of these, we have polyvinyl chloride, which causes us huge problems in production, for example, in extrusion, if we have small quantities mixed in. So we can see that the mixed streams are hard to avoid, because even if we sort out by type, by product type, we still get a variety of plastics that those materials could be made of. And I also brought some examples, dishwasher and monitors, the different materials used, and then in automotive, you all know we have a huge variety of plastic parts in there. A lot of technical plastics. We're going away from the polyolefins, or more away, but we have all these different materials that are used. And so how can we then separate and identify these materials? And a lot of you already know that the typical identification methods, we use infrared spectroscopy or differential scanning colorimetry, which I will talk about more. But look at the numbers of packaging produced in the European Union, the 20 million tons I showed before. Almost 18 million tons are already collected, which is a huge success for us as a community, I think. And 40% of those collected materials are recycled, so they are somehow put back into the material stream. 40% are used for energy recovery, and 20% are still landfilled. And as you know, in Europe, we're going towards zero landfilling, so that number is likely to go down, and we want to see more and more in recycling. And out of all the packaging waste, polyethylene terephthalate, PET, has the highest recycling rates of all plastics, followed by HDPE. And the reason for that is really the products that are made out of it, because PET and HDPE in form of bottles is easy to sort out. So that's why, to this point, it also has the best recycling rates. So how does the recycling process for PET look? We start with the consumer, we throw it away. It's somehow collected in a system, the green dot system, for example, and brought to a material recovery facility where it's then sorted. Paper, glass, metal, and plastics are all sorted out and ideally already separated in particular plastics. As I said, mostly PET is sorted out, and then that is brought to plastics processing facility. Sometimes the first part is already done in a recycling facility. Sometimes it's done at the producers, where the original products are shredded, washed, cleaned, and fed back into the manufacturing process, and a product is produced out of it. Here we show a yogurt cup. And in a study that we performed here at Netsch, we took a bunch of regrind that you can see here on the left, and we knew in general it should be polystyrene. And we just optically looked at the material, and you can see the gray, the dark gray and light gray or blackish particles, and you can see some of the colored ones. Obviously, even the black particles could be different materials, but for the purpose of the study, we picked out the different colored ones to look at what material that actually is. So we used a differential scanning colorimetry for it, and those of you familiar with the technology and Netsch, the DSCs that we have are heat flux DSCs, where we measure the difference in heat flux between the furnace and a reference, and the furnace and a sample. And by comparing the two, we can get information about effects that vary between reference and sample. In this case, a first order transition that allows us, by distinguishing between an endothermic and an exothermic process, to see if the material actually is melting, has a glass transition, maybe thermal degradation is happening, or how the material crystallizes, what polymerization reactions are happening, or for thermosets, what curing reaction is happening. And the other thing we used in this study was our Identify database search system that can be used for material identification. You see some screenshots, and I'll talk more about that in a second. then we have implemented a quality control system that tells you good agreement, passed. If you under a certain threshold you failed, and also using data mining functions, so you can look in your own material database that you can create and use Identify for, but you can also use our databases, simple ones or more advanced ones that you can also purchase additionally if you use that function a lot. So we started with establishing the baseline. We picked some of the black and gray samples. Here you see 4 different measurements that we did, and we ran a DSC at 10 Kelvin per minute up to, as you see here, 140 degrees C. And we looked at the characteristics of these curves. We can already see it's an amorphous material because we see a glass transition temperature. And we also see that this glass transition occurs always in the same range between 92 and 93 degrees C. And by comparing it with our database, we learned that this is a polystyrene. So we included all these measurements additionally and created a new material, which we called polystyrene recycled. And all the other measurements we do will benchmark exactly against these measurements and then know if a material passes or fails. So we have our baseline. Next, we took one of these orange recyclate pieces and we ran the DSC measurement, and we had it compared with the database entry. And you can see that we had a very high agreement with the recycled polystyrene. So we can say the orange sample that we picked is also polystyrene. Next, we took the blue recyclate. We ran it, and we see we get a fail. So there's no agreement with the polystyrene, which is obvious because it's not an amorphous material here. We have a melting peak, so we have a semicrystalline material, and so we just ran the database against it to identify what material it's most likely to be, and we got a very high agreement with polypropylene. So we know the blue sample is the polypropylene. Then we took a red little pellet, and here I'm showing the DSC curve again, because first we also see no glass transition, so we can already imagine that it's not a polystyrene. But other than the previous example, it shows 2 distinct endothermic effects. And from the previous example, we can already get an idea that this is likely a polypropylene. But we check it against the database, and we see, yes, we get a very good agreement with polypropylene for this first peak, or the highest peak. And then we also ran the smaller peak against the database, and we got a good agreement with HDPE. So that tells us in that red flake, we have a large portion of polypropylene and a small portion of HDPE. Because it's so small, I would actually call it a contamination. And what I wanted to point out here as well is when you know your sample weight, and you know the sample weight, and you can always look that up, of the sample from the database, even if you don't remember it, you can already get a very good idea from the area under the peak how much of the HDPE is in the polypropylene. So the DSC method is not only useful to identify materials, and we have here a very fast screening method, but it is also helpful to quantify how much of a material is in your composition, which is another very helpful thing. Again, it helps if you have a baseline for that comparison. But now that we said, okay, is it possible to identify and know what we have in there? my question that I wanted to pose was, do we always have to separate these material mixes, or can we actually do something with these mixed recycling streams? Now, again, I want to look at some examples from real applications, and what kind of blends and material compositions do we have in the automotive industry. So we use a lot of different materials in automotive, but we also have real mixtures happening, either because the material, two components are combined with a snap fit, or they could be overmolded, and so we cannot non-destructively separate the two afterwards. So they're really combined, and that could be the case in the middle console, where we have a blend of polycarbonate ABS, which is very typical, a nylon, a POM, or polycarbonate. Then the air outlet is typically a PBT and POM, and some of the buttons here are nylon and POM. So these parts are very hard, if not impossible, to separate. And then in addition, they're often painted or coated. So with some of these components, if we want to recycle 100%, we really have to look at how we can use these material combinations for other applications. And the second industry I wanted to talk about is packaging. I've mentioned that a couple of times. Packaging makes really up a lot of our plastic in the waste stream, and the polyolefins itself, biggest components, they have such a close density that they can normally not be fully separated by the typical sorting mechanisms that we have, like the flotation method. And so if we look at some mixtures that we have in the same product, the squeezable bottle, for example, that is often around 80% LDPE, and then the cap is polypropylene. So we have a mixture of 80 to 20. And detergent bottles is another example where we have a mixture of HDPE and polypropylene. So again, the bottle and the cap, and the mixtures can vary in proportion from more HDPE to more polypropylene. And now I'm going into a study that we performed at the University of Wisconsin-Madison while I was still a professor there, and it was Dr. Onate who did that as part of her PhD study. So there's a lot of papers out there. If you're interested in a lot of details, either reach out to me and I can direct you there, or you can look her up and you'll find publications on that topic. And what I wanted to show in the next couple of slides is results on a study of polypropylene and LDPE that we performed. So here you see we made artificial blends in different proportions in a twin screw extruder, and then analyzed the resulting blends. We used virgin material, regrind, a combination of the two, and I'm just showing some excerpts from these measurements and analysis. We used again a DSC 214 polymer because it's a very fast instrument and very suitable for polymer analysis. I'm not showing you every DSC curve that we measured. I'm showing you the compounds that you can take away, the key messages that we have here. So on the right, you see a graph of the melting behavior, the heat flow as a function of temperature for 100% LDPE in green, 100% polypropylene in black, and then the blends of different compositions in between. And we can see the melting temperature of LDPE is at 111 degrees C. And as we're following this dashed red line, we see that this temperature, the location of the temperature, really stays unchanged in the blend. When we look at the melting peak of polypropylene that happens at 160, that is slightly shifted when it's blended with polypropylene, but it's still possible to identify it as a polypropylene. The other thing we see that I pointed out earlier Obviously, when we have a mixture and we use the same sample weight in our DSC measurement, the area under the peak, the enthalpy will be different. And based on that, we could actually recalculate what the proportion of material was in that particular sample. Obviously, it's something we determined by our blending compositions. But if you don't know, I wanted to point out again, it's a way to quantify how much of a material is in there. And then we also wanted to look at the crystallization behavior. Here you see again in green, the LDPE crystallizes at 98 degrees C, the polypropylene at 160. So polypropylene, as we're cooling, crystallizes faster. And we see that the polypropylene peak in the blend is almost not affected. It's the material that crystallizes first, but we see that as soon as we have really high proportions of LDPE in our blend, the crystallization of the PP seems to be affected by the LDPE. And when we look at the peak of the LDPE, we can definitely see that regardless of the blend composition, it's already shifted to higher temperatures because the crystallization is affected. That is obviously something we have to take into account when we work with blends, intentionally or unintentionally, because then the identification might be obscured by these effects. And to highlight why we can learn this effect of the individual components on the crystallization of the other from a DSC curve, but just for the sake of this presentation, I want to show you that we used other means to study this effect, and we used hot stage microscopy that you wouldn't do in production setting, but you can do in a research setting. And here you see at the bottom the LDPE crystallized at 100 degrees C for 20 minutes, and you see the spherulite structure, the very fine spherulites that we get. And a little blurry, not as sharp as, for example, the polypropylene that was also crystallized for 20 minutes, but at 125 degrees C. So very sharp, relatively big spherulites, characteristic for PP. And then on the right, you see crystallization images, all taken at 125 degrees C in time intervals of 4, 8, 10, and 20 minutes, and different compositions. And here I really want to point out the right column. You see when we have the conditions to crystallize the polypropylene, by having 75% of LDPE in the mixture, the crystallization of polypropylene is highly affected. The spherulite structure that we get is much finer and not as sharp as we would have it with just the polypropylene. And even with 25% of LDPE, we can already see the spherulites of the PP getting to the size that we would expect, but they're getting more blurry, less defined. So the effect that we see here, I just want to go back real quick. The PP crystallization, we could already see that's affected by LDPE being present in the blend, and the LDPE crystallization definitely is happening earlier because the polypropylene is acting as nucleation sites. And the microscopy is just stressing that fact. The next aspect I want to talk about is rheology, because I find it a very, very powerful tool to study recycling and behavior of recycled material, as well as intentional and unintentional blends. And for the typical way to study these effects would be at lower shear rates. So we would use a rotational rheometer, in that case, one of our Kinexus rotational rheometers. And just very briefly, I want to talk about the principle of rheological measurements, where we obtain information about the shear stress, shear strain, and shear strain, the strain rate, by sandwiching a sample between two parallel plates. And we move, for example, in this case, we move the top plate with a velocity u, and then it experiences strain or shear rate depending on the stress we apply here on the top plate. And we get a shear profile. And because we can't really shear two parallel plates continuously, eventually they would just fall off, we do that in rotation, which is depicted below, where we have a top plate that's rotating on the bottom plate and is actually causing that shear profile. And then if we do that in rotation, we can obtain the viscosity values, so how well the material flows by the ratio of shear stress over shear rate. And if we do that in oscillation, we test more the viscoelastic properties, and we get the modulus, the shear modulus, as a function of shear stress over shear strain. So that's just really the basics. And what we can use that for to study polymers in general, both rotation and oscillation, we can learn about the viscosity and the shear thinning behavior, which tells us something about the flow behavior. Then the glass transition temperature and the entropy elastic behavior, also the viscoelastic behavior, which is relevant to understand processing characteristics. When we think of recycling and blends, the molecular weight distribution is a very important information that we can get. Relaxation time as well, that has something to do with bonding and adhesion. And then, as I pointed out, miscibility and compatibility is one of the most important factors for blending behavior, because it already gives us an idea if something is compatible, it's very likely to also have the benefit in other properties like the mechanical properties. And gel point for thermosets. So in the next couple of slides, I want to focus on the zero shear viscosity, molecular weight distribution, and miscibility. For some, I'll only show you some schematics because we're not always able to share what we measure for customers, but I still wanted to give you that information. And that is how the viscosity function tells us something about the polymer structure. On the left, you see viscosity as a function of frequency or shear rate for 3 different molecular weight materials. And you can see that with increasing molecular weight, the curves are shifted to higher values. So we get a higher zero shear viscosity. So that's a sensitive measure of molecular weight. And why is that so interesting if we're talking about circular economy and recycling? Because as a consequence of the reprocessing of the material under thermal oxidative stress, we can see degradation in the form of chain scissions and chain length reduction, and sometimes also condensation reactions that would increase the viscosity. And we can already learn significant information just from viscosity curve. The other thing is, if we look at the same measurements and we would investigate different with the same molecular weight, the same average molecular weight, but a changing molecular weight distribution, we would see that the length of the Newtonian plateau depends on the width of the molecular weight distribution. So again, it's very hard to compare 2 different materials, but if you're looking at regrind, you can already see how different that material is from your virgin material or a composition of virgin and regrind. So that's why I wanted to mention that. And that is measured in rotation. And if we measure in oscillation, because we want to get other information, then the increasing molecular weight actually shifts the curves to lower frequencies. And so also this crossover point would be shifted. But that's just additional add-on information. Now I want to talk about the compatibility, and the rheological measurements we did are pretty straightforward for a lot of plastics materials. We used a standard 25mm plate diameter, varied the frequency, had a low force, a strain in the linear viscoelastic region, and a gap of 1 millimeter. And all the results you see are shown as a function of shear rate, because we could use the Cox-Merckx rule to convert frequency to shear rate. And the first curve I want to show is the flow behavior of virgin and regrind material. In the black curve, you see the virgin polypropylene, and in the gray curve, you see the regrind polypropylene, so the same type of material, and you see the shift in zero shear viscosity tells us that the regrind underwent a reduction in molecular weight. And we also had the advantage to be able to use GPC to confirm, and you can just see at molecular weight there was a significant reduction that happened during the processing step. So just from that we can learn something about that rheological behavior tells us about the molecular weight, but in the end, for processing, we really want to know how the flow behavior is affected. And that's why, in my opinion, it's very practical to determine the rheological properties and get additional information about the molecular weight distribution. Then I want to show some measurements on the blends that we investigated. So again, blends of PP and LDPE. Measured at the same temperature, we see that the polypropylene has significantly higher viscosity than the LDPE. And we can see with the blend materials in between, the blends fall between the PP and LDPE. The higher the PP content, like the pink curve, the closer that behavior is to polypropylene, and the higher the LDPE content, the lower the viscosity. And you can see that for the zero shear viscosity, the rule of mixture doesn't really apply, but we could show that at shear rates of 50 reciprocal seconds and higher, the rule of mixture really works well. And if we want to study miscibility or compatibility of blends, that is also possible with rheology, because it's very sensitive to the molecular structure and the phase behavior. When I talk about miscibility and compatibility, I don't put a picture in here, but it tells us if we have distinct phases or if we have a really good adhesion between the materials, it behaves like a homogeneous new material, and that will have a huge effect on the mechanical performance. There's a variety of different techniques to investigate the miscibility of materials. The two most used and most suitable for a lot of plastic materials are the ones I'm showing here. On the left is what we call the Hahn plot by Professor Hahn, which is a plot where we have the logarithmic storage modulus as a function of the logarithmic loss modulus. And if we have just a virgin material or a miscible blend, then the relationship is just a straight line. If we have a blend that is immiscible, we see a deviation from that straight line. And on the right, you see the Cole-Cole plot, where we have the viscous portion of the viscosity over the elastic portion of the viscosity, and that follows this this curvature. And if it follows this curvature, we can also know it's miscible. I personally, if it works, prefer the Hahn plot because it's a little easier, but I want to show you how that looks for the different blends that we investigated, that Dr. Ohnate investigated. You see on the left the Hahn plot. You see in green and black the boundaries of our LDP and PP, no blend composition, and you see that all the blends fall in between these two. We have a linear relationship that indicates to us that all blend compositions of LDPE and PP that we studied are miscible. And the same when we look at the Cole-Cole plot, it also shows us that LDPE and PP are the boundaries, and the blends are in between, and they follow this shape, which tells us that the blend is miscible. And to really show you that can be applied to other properties, I'm also showing you the mechanical performance of these materials and their blends. We did mechanical tests on dog bone specimens, and here you see the tensile stress is a function of the tensile strain, and you see the typical more brittle behavior of the polypropylene, higher strengths, less ductile, LDPE, lower strengths, more ductile, and the blends fall in between. So you see a combination of the properties of PP and LDPE combined in those blends, and depending on the proportion, you get more of the PP behavior with some of the LDPE behavior and vice versa. The only thing that's slightly different is the blend with the high LDPE content. It seems as if we are not just getting a combination of the two, but even an advantage. So this material has a higher strength than the pure LDPE, but it also has a higher ductility. So that could indicate that this blend is particularly interesting for applications where you need slightly higher strength and higher ductility. So when we look back at the motivation that we originally had, we wanted to know if natural blends in packaging actually make sense. And the DSC, we already saw, yeah, blending seems to work, and we can distinguish between the different components. But when we look at the compatibility, we need to look at the proportions that we have, as I said, that occur naturally in products. And I have the example of squeezable bottles where we have 80% LDPE, 22% polypropylene. And as you just seen, all blends of that composition, regardless of the proportion, are compatible. So that is something that could be used in a new material, in a new application, without separating it. For the detergent bottle, I mentioned that the proportions are different, and Dr. Onate's study showed that a compatibility between HDPE and polypropylene really exists if HDPE has higher contents than 50%. So that also gives us an indication what material blends make sense for us to use, and which we should stay away from because they're not producing a good new product. So to conclude all of this, I hope I could show you that thermal analysis and rheology can be used to characterize pre-consumer and post-consumer waste. And it can help us to screen for further processing. The DSC method, hopefully I was able to convince you that it can be used to characterize and separate recycled material in single and mixed waste streams. That by having fully automated curve evaluation, as we have AutoEval with our DSCs, and material identification and a database system, it's really easy to differentiate within your recycled materials. Having an auto sampler, you can go through a lot of samples really fast. At this point, I also wanna mention that what I've shown you today is mostly on blends where we have relatively high proportions of two different materials. When you think of contaminations, the contents would be lower, and it's a little harder to detect. But as you've seen in the example of what we call the polystyrene recyclate, we had that PP with HDPE, even in a small proportion, the DSC was sensitive enough to pick up the HDPE. And then when the base material is known, I think that is very valuable, and I've used that a lot in my own practice. is that you can calculate the material proportions from the peak area. And I also hope I could show you that rheology can be used to understand the effect of degradation when you reprocess a material and what that could mean for your processing behavior, for extruder, injection molding settings, and that it can be used to screen blend compositions for processability, for example, using compatibility to already get an idea about the mechanical performance, even if you don't measure the mechanical performance. In a lot of cases, we want to have one measurement to avoid having to measure all of it. And I think thermal analysis and rheology are good tools to do that. If you want more information after you think about this webinar for some time, you can reach me or send your questions to webinar_ngb@netsch.com. And as I said in the introduction, please also feel free in the questions, put additional topics about recycling that you would be interested to see. If you want to know more about auto evaluation, if you have the challenge of having to identify material that have very close melting peaks, and you actually get something like a double peak and you need peak separation, we have software for that. So depending on the topic, just leave me a note in the messages, in the questions, and I'll make sure we have additional webinars for you on those topics. And with that, I first thank you for your attention, and I would also like to thank you for all the questions that I'm getting. And I'm just starting to look. The first are just that you were able to hear me, which is good. Just in general, I have that question a couple of times. The slides and even the video of that presentation will be made available to everybody attending and registered. So you should have that. Then the first question I have, sorry, it looks, okay, so there's one general question, why we use the twin screw extruder for blending, and that is really, for the blending, we want to get elongational stresses to really get a good mixture, and in a twin screw, you can really achieve that much better, because especially if you have co-rotating screws, at the nip point between the two screws, you get really good elongational stresses, and that helps with mixing. So that's why a twin screw extruder is preferred. Yeah, then there was the question about should we expect a melt temperature, melt peak, if HDPE and PP as a blend are miscible? Oh, I guess that means if we have miscibility, shouldn't we have one homogeneous melt peak? That really depends on the material. With some materials, if they have a close melt temperature, then you can really start to see one peak. But if the two materials really have distinct characteristic temperatures, you won't see that. I'll just try to go back real quick to show you this with the crystallization behavior. You see it a little bit. So with the PP and LDPE, the peaks are really moving closer together. But for the different spherolit structure and the distinct different melting temperatures of almost 20-degree difference, it's not happening that we get one uniform crystallization or melting peak. So that depends on the material. HDPE and LDPE, for example, have very similar melting and crystallization temperatures. So there you could get one homogeneous peak. But I have no examples of that to share, unfortunately. Okay, then there's a question if the molecular chains are also affected by the shredding that can happen in recycling. And that is very rare and not critical. You have to think of that more like the pelletizing process when the pellets are produced the first time. The mechanical shredding does not really always cut the molecular chains in the middle, because you have to think of it as really this entangled mess of long molecular chains, and the probability of cutting one of those in half is just lower. But the thermal stress that acts on it, that can have that effect of degradation that leads to molecular chain reduction. The difference between compatibility and miscibility, there is that's a good question. In general, they're often used in the same context, and I don't want to go out too far because I'm not as deep in that particular topic right now, but it has something to do with the phases of the material, which is the phase enclosing, which is the enclosed and the enclosing, like a matrix and a filler system. But in general, there is not a real big difference between the two terms. There's a small difference in how the phases are, which is the dominant phase. Then I have a question about the sensitivity of the method. It's not 100% clear which method the viewer is referring to. So I would just say DSC is a very sensitive method. Rheology, it always depends also on your baseline. If you have very, very small changes in molecular weight, for example, the effect of temperature could be higher than the change in molecular weight. But overall, even slight changes are normally detected, that there is a change. I wouldn't always look at the absolute values when it comes to the viscosity curve, for example. I wouldn't say because it's 20% lower, that means a 20% reduction. You cannot really say that. You can only look at trends. I hope that answers the question. Then okay, then the next question is how do you calculate the proportion with the peak area in DSC? And that has something to do with because the viewer asked, because the peak is only related to the crystals, and so you normally have to look at the second heating. The first heating gives you the information or cooling, the cooling behavior, and the second heating. Sorry, let me rephrase, that might come out confusing. So if we do the first heating, what we really look at is the processing history, and that tells us something about how the material crystallizes during processing. If we look at the crystallization peak or the second heating and the melting peak, we really get the unique fingerprint of the material, and that's what you should use to calculate the proportion of the peak area. And for that, you need to know the sample weight of 100% of that material, and then of your of that peak that you have in the blend. And just by how is that called in English? Sorry, by just putting your peak of the pure material as 100%, you can calculate what the peak in the blend equals in percentage to that. And then knowing the weight, you can calculate out of the percentage the actual weight proportion. I hope that that was clear enough. Yeah, then the question is, how low is the threshold of contamination to be able to be determined? That's another really great question, and I actually want to stay on these slides because you already see the different materials, because of their molecular structure, have different enthalpies for melting and crystallization. So the lower the melting enthalpy of a material is itself, the harder it is to detect even smaller quantities, and you can go up with your sample weight to eliminate that factor to a certain degree, but obviously you can't go up to super high weights because then your heat transfer within the crucible is getting in the way, and your measurement is not as precise anymore, right? There's this balance in sample weight to really get a good measurement, but if it's possible, you can slightly increase your sample weight to make sure that you can also pick up smaller traces of a material that overall has a low melting enthalpy. I personally haven't done much on recycling rubber. That's a question here. I really only know that rubber can be recycled if there's still some active functional groups and you can add more sulfur into the mix, and then it's shredded and the vulcanization is triggered again. But I'm not an expert on rubber, so I have to skip that. Can't talk in more detail about it. Then we have another question about the threshold. I think that might be something interesting for more additional information, also showing you some measurement results. Yeah, so there's another question about the overlapping of peaks. I hope I answered that already sufficiently. The temperatures that can be achieved with the rheometer, we go up to 450 degrees C, and with the capillary rheometer that could also be used even a little higher. So you can analyze materials like high temperature, high performance materials like polyether ether ketone. Okay, then this is a very important question that I might not be able to answer because it's a question that the whole industry is asking. But I want to mention it here because it's worthwhile to think about it. And the question is, in a real plant application, for sake of separation among different plastic materials, do I need to treat all of the waste mass? And how can I be sure the sampling is really identifying the mean composition of the waste mass? That's a very realistic problem that we're facing. So if you have a lot of regrind, I pointed that out when I said what materials in packaging, for example, could be made with PVC. Even very small quantities of PVC can ruin your whole batch. So that is very critical. And obviously we can't do 100% screening. We have to work with a certain sampling rate. And from my experience with processors working with regrind material, they do higher sampling rates, and they make sure they take it from different batches and different locations of the batch, for example, that they receive. They often, if they use DSC, use an auto sampler that they can measure a lot of samples relatively quickly. But overall, it really only can be established over time if you have the same supplier of your regrind material, for example, that through the statistics you learn how much of your material you have to sample. Obviously, it's a problem that you can't sample 100%, and you can have even small traces of contamination creating a problem. But I would say that's something that we as a community have to work on together. There's no straightforward solution for that yet. Then there's a question about the sensitivity of using DSC for material characterization or identification compared to FDIR. We definitely, both technologies really work to tell you what has happened, what kind of material you have. The FDIR gives you the information of molecular groups. So it has the benefit if you expect degradation and you really expect a change in your functional groups. It might also be able to give you that additional information. I, in my practice, like DSC because it gives me the identification, and it also allows me to learn more about how much of the material is in there. So the quantification for me is more relevant. So it really depends on what your what's the most important thing for you. Yeah, then someone asks if you can identify material in multi-layer packaging. For sure, that identification is something that can be done with the DSC. Then if the TG of mixtures is similar, is that similar to melting, separate, or only one TG? Again, that depends on the material, similar to the melting and crystallization behavior. And then there's the question if there's any database with the characteristics of the main plastics, glass transition temperature, crystallization temperature. There definitely are different databases that you can purchase from that search through data sheets from material suppliers and offer a compilation of that. Just if you Google, you'll probably find MadWeb and others. For some of these, with respect to crystallization temperature, that's already something that is often more specific. You often get glass transition and melting temperature. We, for example, offer databases that have a huge variety of plastics and their thermal characteristics in them, and you can get that with the DSC or afterwards with the DSC from Netsch. We offer that as a product. Yeah, and yeah, the last thing is, that's a little bit off topic, the working principle of the hot stage microscope. That's really, you put a small quantity of material between two glass plates, put that in, it's a little box, a heated box in your microscope. Cooling rate is relatively low. Isothermal measurements are ideal. Cooling rate, I think you can achieve is 3 Kelvin per minute, maybe lower, maybe 2 Kelvin per minute. And then you look through that heated chamber. It has two glasses, and you put your sample between two glasses in between, and then you look through that whole composition, and you can follow the crystallization like that. So it's called hot stage microscope. Just look it up, and if you're interested in getting something like that, you can Google it and find it. With that, I'm at the end of the questions. Thank you very much again for your attention. I hope you enjoyed that presentation and you got some valuable information out of it. Feel free to reach out to me or us if you're interested in more topics to learn more about the specifics of some of the measurements. I'm already taking away that combined peaks and peak separation might be an interesting topic, and so make sure to look out for that, and we even might send information about such a webinar to this list of recipients. thank you very much, and I hope you you enjoy the rest of your day or evening. Thank you very much. Bye bye.